We continue our discussion on linear programming in this video, and this time we take a look at algebraic solutions. We will take a look at one example in this video, and then a brief look at the simplex method. The content of this video is somewhat more intricate than that of most other videos. If you find it too difficult for your mathematical background, I think you can skip it and remain only with the geometric intuition for linear optimization. However, this video does lead to the simplex method that I only introduced briefly. That's a very popular and efficient practical method for linear optimization. Remember from our previous video that the objective function will always find its maximum and minimum value at the intersection points of the constraints in case the feasible region is bounded. So we first have to find the intersection points. And for this, we will have to consider all pairs of constraints. We will then verify all intersection points to see whether they are feasible. And this will give us the extreme points. Finally, we will evaluate the objective function at the extreme points, and we will find the optimal value in one of them. This is a graphical way to understand the approach. The green area is the feasible area that we find out by considering all possible pairs of constraints. We then calculate the value of the objective function at the corners of the feasible area, and we find the optimal value among them. To see this in terms of equations, that is to say in an algebraic setting, it's easiest to consider only problems with two variables. The same can be formulated also for more variables. We can easily assume that all constraints are linear inequalities of the form a1x1 plus a2x2 is smaller than or equal to b, where xi are greater than or equal to 0. And this can be transformed into an equality by simply adding a new variable y1 taking non-negative values. And this of course can be done for all other inequalities by adding a new variable for each of them. So finding the intersection points of two constraints comes to solving a system of two linear equations over non-negative variables. Some intersection points will be between two constraint lines, meaning where the y variables are 0. But other intersection points will be between a constraint line and a coordinate, meaning that a y variable and the x variable will be set to 0. And finally, obviously, an intersection point will be the origin, in other words, the point where both x1 and x2 are equal to 0. So in other words, for any pair of variables, we set the pair to 0, and then we solve the remaining system of n equations with n variables. Just to clarify this idea, here comes again our carpenter example. Recall the carpenter's problem. We were supposed to maximize 25 times x1 plus 30 times x2 such that 20x1 plus 30x2 is smaller than or equal to 600, 5x1 plus 4x2 is smaller than or equal to 120, and x1 and x2 are greater than or equal to 0. Here, for simplicity, I'm assuming that there is no pre-existing contract. We convert each of the inequalities into equations. So in our case, this becomes 20x1 plus 30x2 plus some new variable y1 is equal to 600, and 5x1 plus 4x2 plus y2 is equal to 120. And all the variables, including the new ones, are greater than or equal to 0. So consider the set of the new variables x1, x2, y1, y2, and for all pairs of variables, set the chosen pair to 0 and solve the resulting system of two equations with two unknowns. And we have 6 possibilities. In the first case, x1 is equal to x2 is equal to 0, and in this case, the two equations we have lead to y1 equals to 600 and y2 is equal to 120. In the second case, we set x1 and y1 to be 0, and in this case we obtain that x2 is 20 and y2 is 40. In the third case, we set x1 and y2 to 0, and we obtain x2 equals 30, and y1 is equal to minus 300, which is an unfeasible point because y1 should be greater than or equal to 0. In the fourth case, we set x2 and y1 to 0, and again we obtain an unfeasible point. y2 should be in this case minus 30, which is impossible. In the fifth case, we set x2 and y2 to 0, and we obtain x1 to be 24 and y1 to be 120. Finally, in the sixth case, we set y1 and y2 to 0, and in this case we obtain x1 to be 120 over 7 and x2 60 over 7. Here is the same picture using the more intuitive geometric intuition that we had in the previous video. So to summarize the algebraic approach, the idea is to enumerate all intersection points of the constraint lines by solving a number of linear equations. And then, if we have m variables, consider all possible combinations of m unknowns, set them to 0, and solve the remaining system of equations. It all sounds good, and hopefully clearly enough justified by the geometric intuition we had before. But here is the trouble. This approach leads to identifying enormously many points and thus solving enormously many systems of equations, which is clearly unfeasible in practice. To make matters even more frustrating, many of these intersection points will in fact be computed for nothing because they will turn out to be unfeasible. And the solution out of this mess is the famous Simplex method. This Simplex method has been proposed by George Dantzig already in 1947. We know now that historically the method has been developed even earlier, independently and secretly, by Leonid Kantorovich in 1939. John von Neumann is also another independent contributor in 1947. As a historical note, Dantzig's solution was in fact given to two open problems in statistics when he was a graduate student at Berkeley in 1939. The input to the simplex problem, or simplex algorithm, is a linear program, meaning a linear objective function and a set of linear constraints to be satisfied. The simplex algorithm is one of those that are quite intricate to explain in a short video, and so here I will only tell about how well it performs in practice, and I will leave out the details of the method. The starting point is to think about the objective function as a constraint function so that we only deal with constraints throughout the problem. To do that, we introduce a new variable z and make it equal to c times x. We will simply aim to maximize variable z. This brings the problem to the so-called standard form, and I will skip all the details about the simplex algorithm. Simplex is well known to perform well in practice, even though it's known to be exponential, meaning very slow in the worst possible case. This has been intriguing for a long time already, that it works so well on real-life problems, even though we can find artificial examples on which the method becomes so slow that it's impractical to use. We stop here our considerations on linear programming. In the next video, we will discuss a very different class of problems, widely used in practice, and based on very different mathematics than what we discussed so far in this course.